This lesson is on what's called the law of cosines. So I've derived the law of cosines on a separate video again. It's not a requirement that you watch it, but I think it's worth doing. It's less than 4 minutes. It's not very long. And again, even though you aren't going to be expected to do this for IB, this might give you some ideas when you start thinking about your internal assessment again in 12th grade. So it's worth taking a look at it to get a little bit of a sense of how things work. All right, so again, we've got this triangle ABC with the usual naming convention with the side opposite c's, little c, etc. And then the law of cosines looks like one of these three. This is usually the one that textbooks or formula sheets will report as this one. It basically says c squared equals a squared plus b squared minus 2ab cosine c. It kind of looks like Pythagorean theorem with this extra term here to adjust for the fact that angle c may not be a right angle. But anyway, the thing to remember here is that this lowercase c matches with this capital C. Now, if you knew lowercase c and capital C, you probably wouldn't use the law of cosines. Clearly, this is more complicated than the law of sines. Sine A over A equals sine B over B equals sine C over C. So if you had an angle side pair, you probably wouldn't be doing the law of cosines, although you can. And there may be problems occasionally where you are instructed to use the law of cosines to blah, 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 and therefore you have no choice but to use what they asked you to. But other versions of the law of cosines, again with the triangle ABC, would be b squared equals a squared plus c squared minus 2ac cosine b. This angle b is opposite this lowercase b, everything else is a's and c's. And then a squared equals b squared plus c squared minus 2bc cosine a. This angle a is opposite this lowercase a, everything else is b's and c's. So these are the versions of the law of cosines. Now the textbook also, or in the formula sheet actually, also solved for cosine C and writes another version of the law of cosines. As far as I'm concerned, that's a waste of your time. You can always solve the equation. It's not terribly complicated. So I just do it this way because, again, I like to memorize things whenever possible. And that's the version I think is relatively easy to memorize. Okay, so we are asked in this triangle to find the length of BC. Well, that's that one right there. And of course, it would usually be called little a. Now, this side over here, the 13 is now little b because it's opposite capital B. And the 11 is now little c because it's opposite capital C. And if we're looking for little a and we know angle A, then it has to start with a squared and it has to end with cosine A. So it's going to be a squared equals b squared plus c squared minus 2bc times cosine A. It's this version of the law of cosines we're going to have to use. So a squared equals, well, b squared would be 13 squared, and then c squared would be 11 squared, and then minus 2 times 13 times 11 times cosine of the 42 degrees. Now I'm going to plug all that into my calculator and keep the decimals because it's not the final answer yet. So I get a squared equals 77.4605791. And now I square root both sides. And I don't have to worry about plus or minus because a is a length. It has to be a positive. And I report the answer now with the required 3 sig figs. So I get a is approximately 8.80, and the units here are centimeters. Now I want to point something out to you while you're doing the calculations. You want to be very careful not to do 13 squared plus 11 squared minus 2 times 13 times 11. Because the 2 times 13 times 11 has cosine 42 on it. So these two may be like terms, but this one doesn't match because this one has cosine 42 and these do not. So this calculation can be put together, but then this has to be calculated first before subtracting. Or again, if you're going to use a calculator, just type the entire thing into the calculator once and let the calculator do all the work. So now we have another problem in triangle PQR. PQ is 7, QR is 5, PR is 8. Find the measure of angle QRP. Well, first of all, this would be the measure of angle R that we're looking for. The PQ is lowercase r, the QR is lowercase p, and the PR is lowercase q. Whatever letter is missing, that's the lowercase version of that. Now, if I look at the information I know all 3 sides and I know none of the angles. So I definitely do not have an angle side pair that I know everything about. So the law of sines would make no sense whatsoever here. But the law of cosines could work. If I'm looking for angle R, there's only one angle in the law of cosines. That would be, in this case, I would need cosine of R. But if I want cosine of r, I have to start with r squared, and then equals, in this case, p squared plus q squared minus 2p q, and then times cosine r. So this is the version of the law of cosines I'm going to need to use, and now I'm going to plug the numbers in, the r, the p, and the q in here. So r squared becomes 7 squared, p squared becomes 5 squared, and q squared becomes 8 squared, and then minus 2 times 5 times 8 times cosine of r. Now I need to isolate cosine of r. Now remember, I can't do 5 squared plus 8 squared minus 2 times 5 times 8 because this is a cosine r term, and these are not. So they're not like terms, but I can calculate these two first. And of course I can do 7 squared as well. So that's 49 equals 25 plus 64. And I'm going to do 2 times 5 times 8 anyway, minus 80 cosine r. But again, when I'm subtracting and adding, this doesn't match with anything. So I have to just add these two together. And I get 49 equals 89 minus 80 cosine r. Now once again, this 89, subtract 80 is not okay because this is 80 cosine r. So I have to subtract 89 from both sides and get negative 40 equals negative 80 cosine r. And now I can divide both sides by negative 80. So negative 40 divided by negative 80 is a half. So a half equals cosine r. And now I can use the cosine inverse. So measure of angle r is going to be cosine inverse of a half. When I plug that into my calculator, I get exactly 60 degrees. And so that's my answer. The measure of angle QRP is 60 degrees exactly. And there was no rounding required, so I don't have to worry about the 3 sig figs. Now part B says find the area of triangle PQR. Well, I now know the measure of angle r, so I can use the formula 1/2 AB sine C, or in this case 1/2. Well, let's see, I'm going to have to use sine r because I have no choice. It's the only one I know. So I need to know the sides that are next to r, or the sides that surround r. So that'd be p and q. So 1/2 pq sine r is the formula for area that I'm going to be able to use here. So the p and the q surround the r, or r is included between the p and the q. So it's this formula. So that becomes, in this case, 1/2 p was 5, q was 8, and then I need to do sine of the 60 degrees. And again, I plug that into my calculator and then round to the 3 sig figs. And I get approximately 17.3, and the units are going to be centimeters squared. So now we have the two methods, the law of sines and the law of cosines. So we're going to use the law of sines if we know an angle side pair, angle A and little a, or angle B and little b, etc. So you can use sine A over A equals sine B over B, etc. And then use the law of cosines if you don't know an angle side pair. Well, either you do know it or you don't know it. We don't need another law. The law of sines and the law of cosines takes care of all the possible iterations or scenarios we might have. So the law of sine scenarios would be, this is one of them, where you have this angle and this side, that angle side pair. So this is an AAS. And we know from geometry that if you have AA and S in that order, where S is not between the two sides, but AAS like that, this is a congruence theorem, and therefore any other triangle with the exact same information, AAS, is going to be congruent to this triangle. In other words, there's only one type of triangle that satisfies that scenario. Now, this is an ASA, which immediately does not look like the law of sines because I have this side, but I don't have this angle. I have to have an angle side pair, but once I have two angle measures, I can quickly calculate that third angle. So even though I had ASA and I didn't have that third angle, I could work it out. So really, ASA also can use the law of sines because, again, that third angle is relatively quick to find, and then you have your angle side pair. Now, again, ASA, if I have ASA, these measures of this triangle and the exact same measures on another triangle in that order, those triangles have to be congruent. This is a congruent statement, so there's only one type of triangle that will satisfy that. Now here's a third scenario for the law of sines, and this is where this angle and this side are known, and we're looking for, let's say, this angle. But this is an SSA scenario. And if you remember from geometry, there is no congruence theorem that says SSA. The way I usually say it when I teach is if you spell it backwards, it spells something we're not supposed to be saying in polite company. So this is not a theorem for congruence, and therefore if you have this scenario, this is going to create what we're going to call in the next lesson the ambiguous case of the law of sines. You cannot solve it necessarily uniquely. There may be more than one type of solution to this scenario with the SSA. Now for the law of cosines, if we don't have an angle-side pair, these are the remaining scenarios. So in this first scenario, we have SAS, the angle is in between the two sides, and again, we would be calculating this side, for example, using the law of cosines. But this, once again, is a congruence theorem. So any other triangle with the exact same SAS information would be congruent to this one. So there's only one possible solution. And this is the last scenario, SSS. And again, we'd be looking for one of the angle measures. But once again, this is a congruence statement, SSS, congruence theorem. So, and I think it might be a postulate actually. But anyway, so any other triangle with the same three measurements of the sides would also be congruent to this one. So again, one unique solution. Now there's one other congruence theorem we learned which doesn't really need any of these. So let me show you what that looks like. So that congruence theorem was the HL congruence theorem. Now, because it's HL, hypotenuse leg, we automatically know we have a right triangle. So we're not going to bother with the law of sines or the law of cosines. We're just going to use SOHCAHTOA. We're going to use opposite, adjacent, hypotenuse because this is a right triangle, and those are way quicker, way easier to work with. So the HL scenario, even though technically you could use either the law of sines or the law of cosines on it, you're wasting your time. It's much easier to just use sine theta equals opposite over hypotenuse, cosine theta is adjacent over hypotenuse, tangent theta is opposite over adjacent to solve a triangle of this nature. So again, the law of sines, if you know an angle side pair, law of cosines, if you don't know an angle side pair, and we're going to discover that there is some weirdness going on with this SSA type law of sines problem in the next lesson. And that's the end of this lesson.